Okay, so this is working through the multiple choice of the 2015 Systems Engineering exam. So, instructions for section B, following information relates to questions 1 to 31. All right, and we've got a picture of a lathe and some information about a lathe. It's pretty well labeled and it's reasonably clear. So what's it asking us? In the boxes provided in figure 1, label the effort, fulcrum, and the load on the foot pedal. Okay, so here's our foot pedal. Well, we've got the foot pedal is connected to this crank, which is connected to our axle. A lathe, if you don't know, is a device for spinning a job, and you can use a tool to remove material from the job. That would be a piece of wood or a piece of metal or whatever you like. So what do we got? We've got this hinge connected to a linkage connected to our crank. That's going to turn our axle. So that's going to be our load because that's the work we want done. We've got, I imagine this is where you put your foot because it says foot pedal. So that's you putting in some power. That's our effort. And so what we've got left is the fulcrum, which is the point at which this, because it's a lever, is going to pivot. So question 1, we have load, effort, fulcrum. Grand. Question 2. What's the purpose of the wheel in the design shown in figure 1? Okay, so we've got this big wheel that is attached to our axle. And what is it for? Well, if you've got a wheel and it weighs anything and it starts rotating, it's going to have some momentum and it's going to want to keep rotating. And we call that a flywheel. So if you said it's a flywheel, that would be fine. But if you said something because you didn't know it was a flywheel, if you said something like, the wheel has momentum and helps keep the axle turning, that would be fine too, because think about this situation. You can only put force into this crank and turn this axle on the downstroke. There's an upstroke where you can't put any force in unless you sort of hook your foot underneath the foot pedal and lift it up, which seems really silly. So you need the momentum of this big wheel to keep the thing turning. So any answer that sort of encapsulates that is fine. Question 3, the type of motion for each of the following. Okay, so the wheel is rotational motion, and the foot pedal goes up and down and up and down and up and down, so that's oscillating. So that was question 3, rotational and oscillating. Question 4, name the device labeled mechanical device A in figure 2. Okay, mechanical device A, it is connected to an axle, it comes off at an angle, and it helps you turn an axle, so it is a crank. It's got this linkage here that turns your oscillating motion into rotational motion. It's a crank. That was question 4, crank. Right. Question 5. Calculate the maximum force of the rod if the force of a foot on the pedal in figure 2 is 100 newtons. Show you're working. Okay, I like this. So we've got a lever, and let's just draw out what's going on with our lever. So we've got our fulcrum there, we've got our load here, we've got our effort over here, and when we're working with a lever, we know that the force of our load times the distance to our load is equal to the force of our effort times the distance from our effort. So we have, what do we have? We have the force of the effort is 100 newtons. We know the distance here is 800 millimeters. From the fulcrum to the effort, we know that the distance from the fulcrum to the load is 1000 millimeters or a meter. So the only thing we don't know is the force of the load. So we need to reorganize this equation so we have the force of the load on its own, and then we can solve it. So divide both sides by the distance to the load. Distance to the load. You can cancel out the distance of the load, and then you can rewrite your equation as force of the load equals force of the effort times distance to the effort over the distance to the load. Now, one thing I'm always banging on about is anytime you're working with measurements, convert them to meters. It'll just make your life so much easier. So the force of the effort we know is 100 newtons. Multiply that by 800 millimeters, which is, I'm running out of room here, let me rewrite this so that it's a little bit neater. 100 newtons times 800 millimeters rather is 0.8 meters. And that gets divided by, well, it's 1,000 millimeters, which is 1 meter. So that's super easy, right? Because anything you divide by 1 is just itself. So what's 100 newtons multiplied by 0.8? It is 80 newtons. And if you were to divide 80 newtons by 1, you would find it's still 80 newtons. So that's your answer for question 5 is 80 newtons. That's just right. So question 5b. Calculate the mechanical advantage of the pedal system shown in figure 2. Show you working. Okay, so let's draw this one out. We've got what is actually just a lever. So we've got a fulcrum. We've got our effort where our foot would go, and we have our load at the end where we're doing some work. And we've got some distances. So we know that from the fulcrum to the effort is 800 millimeters. And 800 millimeters, I always encourage you to work in meters. So 800 millimeters, well, there's 1,000 millimeters in a meter. So 800 millimeters is 0.8 meters. And the distance from our fulcrum to our load is 1,000 millimeters, which is just 1 meter. So we know this is distance of our effort, this is distance of our load, and we also know force of our effort, which is our foot. So we know force of our effort as well. Force of our effort is 100 newtons. And we don't know force of our load. But we can find that. And we can find that using our formula, because we know that the force of our load times the distance of our load is equal to the force of our effort multiplied by the distance of our effort. And we want to get the force of the load all on its own so we can find out what it is. So we divide both sides by the force of our load. And, sorry, no, we don't. We divide them by the distance of our load. And we find that we can cancel out the distance of the load on that side, which gives us the equation. Running out of space, so I'm just going to move this along a little bit. Force of our load is equal to force of our effort times distance of our effort over the distance of our load. And so now we can just put in our values. So we remember that the force of our effort is 100 newtons. The distance of our effort is 0.8 meters. And the distance of our load was 1 meter. So what does that work out to? Well, 100 newtons multiplied by 0.8 is 80. And the neat part is that this is 80 over 1. So if we divide, if you divide any number by 1, you get the number. So the answer to this question, the force of our load, is just 80 newtons. So that's question 5b is 80 newtons. Great. All right. New question. Question 6. So what have we got here? Late 1800s, steam engines were used to drive industrial lathes and other equipment. So what do we got? We've got a part of a steam engine anyway. We've got the axle being turned by a steam engine. We've got one wheel and a belt and a smaller wheel, and that's driving our lathe. So this is a pulley arrangement. And if we're looking at this, we can see that we've got a large pulley over here and a smaller pulley over here. So without even going into the question and doing any sort of maths, we can just look at this and go, okay, so we've got a big pulley wheel here and a small pulley wheel here. That means that every time this rotates once, this is going to rotate, more than once because it's, much, much smaller. Think about how much the belt moves around the circumference of this pulley. The belt is moving the circumference of this pulley around this smaller pulley. So this one's going to have to rotate faster, which is a good bit of information to have in the back of your mind as you start sort of going into answering the question, because that's going to help you check your answers and make sure that you're right and you're okay. So this is question 6a, the first part. And it says, calculate the RPM of the lathe axle in figure 3. Show your working. And it's telling you the pulley A is rotating 300 revolutions per minute, or RPM. Okay, so before we plug into the formula, let's just think about this, because a lot of the questions in these systems exams, you'd never actually need to look at the formula sheet. You just need to think about the scenario. So the diameter here of this pulley, pulley A, is 0.45 meters. And the diameter of pulley B, the pulley being driven, is 0.15 meters. Now, if I look at that, that looks to me like a pretty nice ratio. In fact, 0.15 times 2 is 0.3. So 0.15 times 3 would actually be 0.45. So this pulley, or rather, this pulley here, pulley A, is 3 times larger than this pulley. So let's just do this. Pulley A, 3 times pulley B. And because the diameter or the radius is proportional to the circumference, or the distance of around the outside of this circle of this pulley, we can say, or we should know, that the circumference of this pulley is 3 times the circumference of this pulley. So every time this pulley turns once, right, because it's the whole circumference that's moving that belt, it's moving this small pulley 3 times, because this one's 3 times larger than this one. So if pulley A is spinning at 300 revolutions per minute, pulley B has to be spinning at, 300 times 3 equals 900 RPM. And that's, you don't even really need to do the maths at that point. You can just look at the situation and figure it out. But we will look at how to solve it using the formulas, because it's nice to show you working, and the question says show you working. So some of these marks, at least one of these marks, is going to involve you working. So let's look at the formula. So we've got pulley A RPM divided by pulley B RPM equals radius of pulley B over the radius of pulley A. So I'm going to shorten that when I write that out, because I'm not writing pulley A RPM a million times. So I might write A RPM over B RPM equals radius of B divided by radius of A. So here's our formula, here's our situation. Now, one thing you'll notice, or you might notice straight away, is that they haven't given you the radius. They've given you the diameter. And so that might, mess you up. You can, of course, turn these into the radius. The radius is just half the diameter. So 0.45 divided by 2 is going to become 0.225. And 0.15 is going to become 0.0. Hold on, mental arithmetic's failing me. 0.15 divided divided by 2 equals 0.075. And you can use those in your formula. If you use the diameter though, the formula will work just the same, and we've done that in class, because this is a ratio problem. That's all. So I'm just going to plug in the diameter, and I might do some rearrangement while I'm here because I know the RPM of A. I know the RPM. I know the radius of B. I know the radius of A. So let's think about what I can do with this problem. Well, I want to find out the RPM of B and not the RPM of A. So it would be much easier, it'd be much nicer for me in terms of like my formula if I could get B on top. And so what I can do is I can just rearrange this, or I can flip both sides. To give me that formula. So that's pretty good. Then what am I going to do? Well, let's just put in, and we know that the RPM of A is 300, and we know that I'm going to use the diameter. Okay. Now I need to get the RPM of B, or B RPM on its own. So what can I do? I could multiply both sides by 300, and I haven't really left myself enough space to do this. Whoop. And so these cancel out, and now I have RPM of B on its own, and I've got this sum over here. You could multiply 0.45 times 300 and then divide it all by 0.15, or you could divide 0.45 by 0.15 and then multiply by 300. That's the one I'm going to show you here. So 0.45 divided by 0.15 is 3 times 300 equals 900. So the answer here that we just got to with this formula is 900 RPM, which is exactly the same thing that we got when we just sort of thought through the question and looked at the ratio. So the difference in size and the proportion of these two pulleys. Question 6b. Oh, sorry, that was 6b we just did. Now we're doing 6c. So calculate the speed of the belt in figure 3. Show your working. Well, what do we know? We know that, so we want to know the speed of the belt. So in other words, if we were, timing how long this belt took to go from here, how quick is it moving? So how do we figure that out? Well, we know that, let me just draw this out. We know that the diameter of this pulley is 0.45 meters. And we know that it's spinning at 300 RPM, or revolutions per minute. So what else do we know? Well, we know that every time this pulley rotates, makes one rotation or one revolution, the belt has to move the distance of that pulley. So if we know the circumference of the pulley, we can help ourselves out there. Circumference, there's a formula for circumference on your formula sheet, not an area circle. Circumference of circle is 2 pi radius. So that's the diameter. So what's our radius? Our radius is half of our diameter, which is 2.5 meters. 2 pi radius, 2 times pi times 0.225. I've closed my calculator. 2. Where is pi on my calculator? There we go. 2 times pi times 0.225 equals 1 point. Let's just round that down. So we're going to say it is 1.42 meters. So that's every time this belt spins, every time our pulley spins, our belt has to travel the circumference of that pulley, which is 1.42 meters. Now, usually speed is given in meters per second. So if we were just to times this by 300, because we go, oh yeah, it's spinning 300 times a minute, then that would give us the answer in meters per minute. And we don't want that. We want probably meters per second. So think about it. If this is turning 300 times, it's making 300 rotations every minute, then it's making fewer rotations every second, because there's 60 seconds in a minute. So if we just divide 300 by 60, we get 5, which is 5 revolutions per second. Now, if we multiply the number of times it spins per second by what distance it has to cover per revolution or rotation, we should get the answer. So 1.4 multiplied by 5 equals. So it is 7. Sorry, that should be a time, so I'll make that clear. 7.1 meters per second. So that's 6C. What else we got? Oh, and they even tell you that. So they tell you they want it in meters per second. They're very clear. So make sure you look at these little things. Make sure you look at the units. In fact, sorry, I missed an entire question. Convert 300 RPM to revolutions per second. So they're stepping you through the process in these questions. I should look at my questions a little bit more closely. All right, we're on to something different. Question 7. Given that the steam engine always rotates in the same direction, how could a belt and pulley system be modified to reverse the direction of the lathe axle? All right, so you want to change the direction of a belt and pulley system. There's actually more than one way to do this, but the simplest one is to do a figure 8 with your belt, because this way, if this is rotating this away, the other pulley will be rotating in the opposite direction. So you could write something like, you could make the belt into a figure 8 arrangement, or you could put the belt on in a figure 8 pattern, or you could cross them. Even crossing the belt over would probably be an acceptable answer. Question 8. Give one essential piece of personal safety equipment that must be used when operating a lathe. Okay, so you're operating a lathe, it's rotating a piece of work, a job, and you are removing material from that job. Straight away, I think to myself, all right, what should I be wearing? Probably some safety glasses, right? So that when the pieces or the chips or the shavings of this job are flying up in the air, they're not getting in my eyes. What else might you wear? I don't know. You might wear boots, work boots, to protect your feet. You might wear a shop apron to protect your clothes, although, again, is that safety or is that just protecting your clothes? One thing you want to step away from with using machinery like this is gloves. If you're using gloves with a machine, you lose dexterity, you lose like how well you can move things and this, your feeling in your fingers. And the gloves are also really good at being caught in machinery and pulled into that machinery. So be very careful when you're being asked about personal safety equipment or personal protective equipment. Think about whether gloves would actually be appropriate in that scenario, or whether they actually would put you in more danger. Anyway, that's question 8. Question 9. What do we want? Question 9. So in a different setup of the steam engine, a gearbox with a ratio of 1 to 4 is used. The question asks us, draw and label the components of the gearbox given that the steam engine axle and the lathe axle rotate in the same direction. Use either the end view or the top view diagram provided below for your answer. Only spur gears from the following range of sizes may be used. Okay, so let's unpack this. They want a gearbox with a gear ratio of 1 to 4. So this means 1. They want the driving gear, or the first gear, or the gear that's connected to, in this case, the steam engine. They want that to rotate once. And for every time that rotates once, they want the output gear, or the driven gear, to rotate 4 times. So straight away, you should be thinking something like big gear, small gear, and this would be 4 times the size of the small gear. Now, what else do we need to think about? They're saying the steam engine axle and the lathe axle rotate in the same direction. So not only do they want a 1 to 4 ratio, they want this gear and this gear to rotate in the same direction. If you mesh 2 gears, I'm doing a really bad job of drawing those mesh. Let's just imagine that they're meshing. If this one spins clockwise, this one will spin counterclockwise. So that's no good. So we need something that will make them spin both the same direction. The way that we do that is we can add an idler gear in the middle. That way, if this spins clockwise, the idler gear will spin counterclockwise, but the output gear, or the gear we're interested in, will spin clockwise or in the same direction as the driver gear. Now, what do we need to do? We know we need a 1 to 4 ratio. So this needs to be 4 times this gear. So what can we suggest? Well, we could have 40 teeth here, and we could have 10 teeth over here. And it actually doesn't matter what size our idler gear is, because our idler gear doesn't affect the relationship between these two. If I use another 40-tooth gear, the ratio is still going to be 4 to 1. If I use a 10-tooth gear, the ratio is still going to be 4 to 1. So that really doesn't matter. So what you need to draw is something that looks like this. Maybe draw the axles in there, that'd be super nice. And you need to label them. So 40, 10, and pick one you like. I like 10, so I'm gonna use the 10. And that's my gear arrangement. So I would need to draw another axle in here. Or you can do that over here. I really don't like drawing gears from above, so I would choose this option. If you're drawing gears from above, you're going to be drawing them. So let's say the axle's like this. You're going to be drawing the gears here, here, and another gear in the middle. And again, you would be labeling those. Right. Great. Okay. Question 10. 10A. So one advantage of using a pulley system rather than the gearbox. Okay, so pulley. Advantages of pulleys. So pulleys are able to slip a little bit. So for example, if you've got your lathe is coupled to this output pulley. If you've got your lathe and something gets stuck in your lathe or it jams up, let's imagine there's something rotating here and it gets jammed, this can slip. That might be desirable because that might prevent your motor, thing driving this gear, from getting damaged. That would be an advantage of a pulley system. Another advantage you might think of a pulley system is that the driver and the driven will spin in the same direction without an idler, which we saw wasn't the case with our gearbox. Another advantage might be that in general, Pulleys are nice and quiet. That might be important, it might not, but it's an advantage. And so that's A. 10B, one disadvantage with respect to safety when using a pulley system rather than a gearbox. Okay, so you've got this spinning laminated fiber belt connected to these two wheels. What are some safety problems with this? Well, the first one that I would think of is that belts can fail. And when a belt fails, you've got this flailing piece of, rubber impregnated fabric or wire impregnated rubber flailing about. That can cause injury. It's also relatively easy to put something into a gap in a pulley system and do yourself some serious damage. If you were to put your fingers in here and the belt was to drag your fingers in around that pulley, that could quite easily, depending on the pulley, of course, chop your fingers off. So there are two sort of disadvantages with respect to safety of using pulleys rather than gearboxes. Question 11. Okay, so how test equipment can be used to measure the RPM of a slowly rotating axle of a steam engine? So this could, you could think of many weird and wonderful scenarios there where you might be able to measure the RPM, or how many times per minute an axle rotates of a steam engine. But if you're just sitting there thinking, okay, I've got a steam engine and there's a wheel attached to that, and I want to measure how many times it rotates. So let's say that's a wheel attached to the axle. So I might say, attach a wheel to the axle, or I might say there'll be a wheel attached to the axle anyway. Otherwise, why would you have an axle? I might say I could put a mark, maybe with chalk, in one spot on that wheel. And then I could start a stopwatch when it is at the top, and I could count how many times does that mark rotate and come back to its original position every minute. And that would give me a really good idea of the RPM of that slowly rotating axle. Right, great answer. Okay, so we've got a steam engine. So the steam engine shown in figure 4 works by having steam forced into either side of the piston by an oscillating rod. The pressure of the steam going into the piston is 10 kilopascals. Okay, so what have we got? We have some sort of steam engine. Here's our source of steam. So here's our high pressure end. Here's this oscillating rod we were talking about. So that controls the flow of steam. Right now it's in the back position. So steam is going to be flowing into this side of the piston. If that oscillating, so it says it's oscillating, it goes back and forth. Maybe reciprocating would be a better. No, oscillating is a great term. So it's going to be going back and forth. When it moves forwards, steam is going to be able to go into this side of that piston and drive it this direction. And that, going back and forth, will turn this wheel, which is connected to some sort of belt. Great. As the axle of the steam engine rotates, steam is forced into the left-hand side of the cylinder, then the right-hand side of the cylinder. Okay, so we just said that. Using the information in figure 4, in what direction is the wheel rotating? Okay, so we said high pressure steam is going through this part. It's pushing the piston towards the right, which is going to be pushing this slide, which is connected to this linkage, which is going to be pushing this crank this way. So it is rotating clockwise. So question 12, we are rotating clockwise. Question 13. So calculate the force on the piston in figure 4 as steam enters the left-hand side of the cylinder. So steam goes in the left-hand side. All right. What's our force? So our force, we know our force is equal to our pressure times our area. So that's the formula we're going to be using. So force equals pressure times our area. Now we know our pressure is equal to 10 kilopascals. Now, important here, and I missed this when I first looked at this question, is that this is 10 kilopascals. Like 10 kilo ohms, kilo represents 1,000. So this is times by 1,000. It's 10,000 pascals. So it's important that we use pascals because here it says pascals. That's our unit of measurement. It's important that we use that in our formula. So we know pascals. We don't know the area, but we can figure it out. So if we look over here, we know that this would be a piston, and a piston is usually a circular thing. And we know that the diameter of that piston is 300 millimeters. So we know that piston diameter equals 300 millimeters. Now, again, I like working in meters. You should be working in meters for these types of questions. So that is 0.3 meters. Now, to find out the area of that piston top or that circle, area of circle, pi r squared. So we know the diameter. We actually need the radius for that formula. So our radius is half of our diameter. So 0.15 meters. So what's our area? Pi r squared. Pi times 0.15 squared equals. So that's 0.07. 0.07 meters squared. Okay, so there's our area. So let's just punch that into our equation. So we've got 10,000. I'm running out of room. 10,000 times 0.07 equals 700 newtons. Okay, so question 14. So why is the force on the piston in figure 4 greater when the piston moves to the right compared to when the piston moves to the left? So let's have a look at that picture. And I've left all this up here to help explain. So when our piston moves to the right, so it's moving, steam's coming through here, here's our piston face, moving over here, it's saying that the force, is greater than when the steam comes through here and pushes the piston to the left. Now, why is that? Well, it's because this side of the piston face, the side that gets pushed when it moves to the left, has this drive rod, this 30 millimeter drive rod through the center. So if you were to look at the face of that side of the piston, you would see something that looks like this. So there's the face of the piston, and here's this drive rod. And what has that done? Well, it's reduced the area of the piston face. Now, if you reduce the area, so this was our area here, if this is less, then when you put it into this equation here, you're going to get a smaller amount of force here. If there's less to push on, you're going to experience less force. So that's the answer to question 14. Might be something like the drive rod reduces the surface area of the piston, would be a great answer. All right, let's move on to question 15. Question 15. So, 15A. State 2 environmental issues that should be considered when using wood-fired steam engine to power a lathe. Okay, so 2 environmental issues. 1, you're burning wood. That's going to create a lot of smoke. All wood smoke is carcinogenic. So you could write, consider the smoke produced, or consider the smoke pollution, or something like that. Issue number 2. What else? You could consider, is the wood from a sustainable source? That is, or sorry, a renewable source even. Because if it's not, then what we're really doing is we're cutting down a bunch of very old trees that can't be replenished within our lifetime, or a single lifetime, to power this steam engine. So those are two environmental issues. Right, two environmental issues that should be considered when using mains electricity to power a lathe. So environmental issues. Number one could be how the electricity is being generated. So is the electricity being generated from renewable sources? So, solar, geothermal, wind. Because if it's not, well, in Australia at least, it's probably from a coal or gas-fired power plant. And they, produce carbon dioxide emissions. So you could write something like the source of the electricity generation, e.g. generating greenhouse gases. And another environmental issue that should be considered when using mains electricity to power a lathe could be, I'm trying to think. What's another environmental issue? I mean, well, how do we generate electricity? We burn coal, so we could be talking about the mining of the coal. So the land that is cleared and damaged in order to remove, coal to power the power plant. It could be the environmental impacts of water runoff from coal or gas mining. They acidify waterways and things like that. So those are environmental issues that you could be aware of. Okay, question 16. State the types of energy present in each of the following. Dry wood. All right, you got dry wood. If you're going to get energy out of it, you're probably going to burn it. So that's chemical energy, right? Dry wood, chemical energy. Steam. Type of energy present in each of the following. Steam. I would say that is heat or thermal energy. I would urge you to stick to the simplest answers when you are talking about types of energy, because you could be cheeky and you could say, well, steam is kinetic energy because we boil water, we turn it into steam, and steam expands and takes up more room and creates pressure, so that's actually kinetic energy. And you would be right, but I would say stick to simple things like heat energy. A spinning wheel, that could be kinetic energy, right? It's moving, it's some sort of active moving thing that you can see. You could also say probably like rotational energy or something, but if we think about movement, we think about kinetic energy, right? So stick with those. All right, I might stop that here, and we'll continue this with the part 2.